So hello and welcome. Just a second. I hope this works now. Yeah. So hello and welcome to this TA session. This is week 4, and so the course. This is the TA session for the course of Physics of Materials, which is an NPTEL course. The instructor for this course is Pratap Haridas from IITM, and I am the TA for this course. My name is Mohammad Tehseen, and I am a PhD student at Aerospace Engineering Department, IISc. So let's begin this week. Let's begin the TA session this week, and I'll start. I have already shared my screen. So let's first briefly review the things that we did last time, and then we will get into this week's content. Okay, so these are the things that we discussed last time. So we started the last week's discussion by talking about uh, electrical conductivity, thermal conductivity, these properties of the materials, and we developed a specific model which is called the Trude model to understand these properties. Okay. So in the week prior to that, just to have continuity of thought, what we discussed in the week prior to that was the same exact same quantities, electrical conductivity, thermal conductivity, but we talked about measurements. Okay, how to measure let's say electrical conductivity, what should be the experimental setup to measure electrical conductivity, and we discussed why in certain cases we use DC current as we use a DC current in the circuit to measure conductivity, and in certain cases we are not able to predict, or the DC current is not the appropriate type of current to be used, for example in ionic conductors, and there we have to resort to AC current to measure the conductivity, right? And then once we measure the conductivity, that's a quantitative value of conductivity that we have from those experiments. Then we would like to inquire what is it inside what happens inside the material that gives rise to this conductivity, especially in case of we concentrated our discussion on ionic solids, and we wanted to know why in the ionic solids we get the values of conductivity as we that we get from experiments. Why do we see those kinds of values? Where does it originate from inside the material? And then uh, once we so that was the motivation for the previous lecture. And other question that we were interested in discussing was if the electrical conductivity of a material is high, does that also imply that the thermal conductivity should be high? Or is there a relation between these two properties? And that's where we develop this Drude model to answer these two questions. First, can we have a model which describes the behavior, electrical behavior of the materials? That is to say, the conductivity behavior. Can we have a model which describes that behavior? And after that, we were interested in answering the second question. That's is there a relation between thermal conductivity and electrical conductivity? And then we made this assumption that there are a lot of free electrons present inside a conductor, and we typically assume that this large number of electrons which are present inside a conductor, that can be treated as an ideal gas, right? And the particle, that's the electrons, the particles in this case, we assume them to be non-interacting, and uh, we make other assumptions for the ideal gas behavior, that there's no interaction between the constituents, and they are far apart. And okay, so for ideal gases we basically assume that pressures are extremely low and temperatures are very high. That is what leads to the ideal gas behavior, right? So we assume a similar kind of behavior for electrons as well, but there's an important distinction, that number of electrons present in, let's say, about 1 meter cube of a metallic sample, it's around, for a univalent metal, the number comes out to be around 10 to the 28 particles per meter cube of a material, while as in an ideal gas the number is around 10 to the 25 or 26 number of particles, atoms per meter cube of the gas. So we see that there's a difference of, or there's a difference of 3 orders of magnitude between these two numbers, and in a way electrons are at most 1,000 times more densely packed than what we typically assume the case to be for an ideal gas. So we have to be careful in using this ideal gas approximation for the electrons. And that's why then we finally said, at the end we close the lecture by making this remark, that in certain cases this Drude model, which is based on this ideal gas behavior, it overpredicts some of the quantities and underpredicts some other quantities. So what we roughly did was we took a box of let's say L dimension, a cube of dimension L, and we calculated that if there's a particle which is represented by red here, in red we denote this particle, and we calculated the pressure that is faced or that is exerted on the walls of this container by n number of such particles, okay, which are electrons in this case. So if there's an electron gas contained within this volume, we calculated the expressions for the pressure that is experienced by the walls of this container, and we got this expression which is shown here. Okay, so basically we calculated the force first, and from that we got the value of pressure. So this is the expression for pressure. Now there are 3 variables here. First is 4 variables actually. First is m, then there's n, then there's l, and then there is px. Okay. So m here is the uh, total mass of each particle, that's each electron, right? And n, this n is the total number of particles. Okay. For example, and this n is equal to small n times the Avogadro's number, where small n is the number of moles. So if we multiply these two factors, we get the total number of particles present in a system. Just excuse me briefly for a moment, please. हेलो, हाँ जी जी, अरेंज हो गया। ओके, जी जी जी, ओके ओके, नहीं नहीं कल नहीं रहेंगे। ओके, थैंक यू थैंक यू। सर मालूम नहीं, मैं एक्चुअली अभी एक लेक्चर में हूँ, तो हाँ हाँ, मैं आपको टेक्स्ट कर दीजिए, कोई नहीं कोई नहीं, आप मुझे टेक्स्ट कर दीजिए, मैं देखता हूँ बाद में। अच्छा अच्छा, ओके, जी जी, मैं उनसे पूछ के आपको बताता हूँ। ओके। Sorry about that. So we calculated the expression for pressure. So this is what the expression for pressure comes out to be, and here we see that mn gives now the total mass of all the particles in the system, and L cube is the volume. So roughly this quantity gives us the density in a way, and then you have this averaged square velocity, okay, or it's also called mean square velocity of the system. And this quantity, roughly it's equal to, not roughly, it's exactly equal to this quantity here. Okay, we are taking all the velocities of all the particles in x direction, say, and we are adding the squares of those velocities and then taking the mean, so it's called mean square velocity. Okay, and then so this is for one dimension. Okay, this is for, let's say, the dimension x, and then we generalize this to 3 dimensions, and we see that the expression only changes by this much. Okay, this is the expression that we see is comes out to be there for three-dimensional model. Okay, and we assume that the averaged velocities are same in all directions, because this is a random, the motion of particles is random in this volume. Okay, so there is equal probability of not a probability but equal statistical average if we take for all the velocities in the 3 directions, they come out to be equal. And then we related this to the ideal gas behavior, and we know the equation for that PV is equal to nRT, and instead of pressure, then we substituted this equation, and this leads us to the kinetic theory of ideal gases, right? And we get an expression for this VRMS, which is the root mean square velocity now, and if we square that, we get the mean square velocity, right? So this is the factor here, and we get it to be equal to 3RT over m. And so here, if we now look at the kinetic energy of one particle, right? So for one particle, this kinetic energy comes out to be this factor, and if we multiply this by n, this gives us the average kinetic energy of the gas, right? So this is the expression for average kinetic energy of the gas, and we can divide it by volume to get the average kinetic energy per unit volume, and this is what the expression comes out to be. for the kinetic energy per unit volume. So this is now like the energy density of our gas, and if we differentiate this energy or energy density with temperature, it gives us the rate of change of energy uh, per unit temperature. So this indicates this differential, this derivative gives us the idea of heat capacity, because this energy is the thermal energy. If we look at the energy expression of energy here, it scales with temperature linearly, right? So this is this average kinetic energy. This is what defines the temperature of ideal gas, and if we take its derivative with respect to temperature itself, that gives us the rate at which energy changes per unit change in temperature, and this is the definition for specific heat, or specific heat at constant volume, basically, because in this whole assumption, in this whole process, there's an underlying assumption that volume doesn't change, right? So how does now this situation apply to electrons? We take a sample, let's say this one, and we assume that electrons are present as a free electron gas inside this inside the space, inside the boundary of the sample, and we just apply the same expression that we obtained earlier, and we get different quantities, right? So basically, yeah, so this is where the Drude model begins, and we basically, for conductance, as we define it usually from Ohm's law, we get it, we define the conductivity as this 1 over resistivity factor, and then we derive an equivalent expression for this conductance by considering it as a free electron, by considering these electrons as particles of a free electron gas, and then we get an equivalent expression for this sigma conductivity, which is given by this expression here, right? Nf, where Nf is the number of free electrons per unit volume, and E is the charge on the electron, tau is the relaxation time, which is the average time between two successive collisions, and m is the mass of the electrons. And if we put in the values, the typical values we get for conductance is this of the order of 10 power 6, and which also matches well with the experimentally determined values of sigma, right, in terms of order of magnitude. And similarly, if we do an analysis for thermal conductivity, we get this expression, and we see this also depends on root mean square velocity, the relaxation time, and there is another factor which is the electronic contribution to the thermal capacity at constant volume. Okay, so this is thermal capacity or heat capacity. So this is the electronic contribution. We are ignoring the contribution due to ionic cores in this term, and then K is the thermal conductivity, which this is the expression for. And then if we put in all the values, we get from this expression that CVE, which is the electronic contribution to heat capacity, it's of the order of 10 power 6 joules per meter cube Kelvin, and the thermal conductivity, it's of the order of 10 power 2 watt per meter per Kelvin. Now this value of thermal conductivity, it again matches well with the experimentally determined values, but this CVE, it does not match well. In fact, it's overpredicted. It's underpredicted by this Drude model. This is not the correct figure. Okay, it should be somewhere around 10 to the power 8. So similarly, so the question is, why is this value correctly predicted by the Drude model, while this value is not correctly predicted, right? So because The reason is because there's another factor called mobility, which gets over predicted by the truth model, and the order of over prediction is by the order of 10 to the power 2, which is the same as the under prediction. By it is the same order of magnitude at which this CE is under predicted, CVE. Okay, it's under predicted by the same amount, same order of magnitude, by as this quantity mobility is over predicted, and when we take a product of them, these two terms settle, and it gives us the constant. It gives us a correct prediction for the order of magnitude of thermal conductivity. Right? So this tells us that Drude model is it's useful in explaining the behavior, but it's not always accurate, right? And there must be something wrong in the assumptions that we uh, have made during framing this model, that is causing this discrepancy between in the quantities. So this is the motivation for today's lecture, that is there something in the picture that we are missing, some considerations that we are missing, and can we formulate a better model which can give us the correct prediction for all of the quantities, right? So with this introduction, let's start today's uh, session. So this is week 4, but let me write the course name first. So physics of materials by, this is an NPTEL 2025 course, taught by instructor Professor Pratap. Haridas from IITM, and I am the TA for this course. My name is Mohammed Tahseen. I'm a PhD student at IISc Bangalore. Okay, and this is week 4 TA session. Week 4 TA session. And the contents that we are going to cover in this week is we will have a look at, so basically we are going to not switch, but go into a little bit more detail into statistical mechanics. And inside the statistical mechanics, we will look at Maxwell Boltzmann distribution, right? And then we will basically point out what are the limitations and we will have some mild introduction, or basically not the introduction, it will be need to consider, what is the need that we need to consider an alternative approach. Alternative approach or alternative statistics. Okay, so this is roughly what we want to do in this session. So before doing that, I would like to briefly discuss some numerical problems related to the discussion that we had last week. So maybe I'll club them with the notes that we made last time so that it's easier for you to keep track of things. Okay. So for example, let's take a few practice questions. Okay. So question 1. So what happens? The question is the mean time between collisions. For an electron in a conductor. What happens to this mean time? Does it decrease with increase in time? Second option, does it increase with an increase in time? It's not time here, it's temperature. Right. Third is it decreases with increase in temperature, and the fourth option is it's a function of position. Okay, which of these is the correct option? So we can pause here for a moment if you want to think about it. Okay, so the correct option for this one is option C, that this mean time between collisions it decreases with an increase in temperature, right? And why does this happen? What is the reason that this happens? The reason is that when we increase the temperature, the atoms or the particles or the electrons in this case, they vibrate faster, right? They vibrate quicker so the velocity increases, right? And when the velocity increases, velocity of their vibration increases, uh, basically there are collisions happen more frequently, right? And the mean time between the collisions that decreases. So let's have one more question. The acceleration experienced by a metallic conductor by an electron metallic conductor in presence of an electric field. And the option is, so the setup is that we have a conductor inside which there are electrons, and we are applying an electric field, and the options are related to what happens to the acceleration that is experienced by these electrons. Okay, and the options are that this acceleration is constant, B, first increases, then becomes constant, option C, first increases, then decreases, and then becomes a constant. And option 4, starts from a positive value and then decreases and becomes 0. Okay, there's someone trying to connect. No. Okay, no one is here. So yeah, so these are the these are the options. What happens to the acceleration experienced by an electron in a metallic conductor in presence of an electric field? And the first question is, its first option is that this acceleration is constant. Second is that it first increases and then becomes constant. Third is that it first increases, then decreases, and then becomes a constant. And the fourth option is, it starts from a positive value, then decreases, and then becomes 0. So which of these options is correct? Now if we look at it, the three options are similar in a way, and one is different from other three options. So if you look at option A, B and C, these have one similarity, that in all of these options the acceleration is becoming constant after a certain transient period. So in first case it's constant in first option. In second option it first increases then becomes constant. In option C it first increases then decreases then becomes constant. So ultimately in all of these three options acceleration is becoming constant, right? And in fourth, acceleration is becoming 0. So if the acceleration of an electron becomes constant, and then in presence of an electric field, the electron will keep on moving faster and faster, right? Because if acceleration is constant, that means velocity is always going up. Velocity is monotonously increasing. So there is no end to where this final velocity of electron reaches, right? There is nothing constraining it. So if there is a limit on the maximum maximum value of attainable velocity, that means that at that velocity acceleration should be 0, right? And therefore the correct option for this one is option D, because electrons cannot accelerate indefinitely, right? So because it's this value of velocity when it reaches some vf velocity, as we discussed. So what happens is basically when you put your conductor in electric field, there's a due to this charge, it experiences a force in electric field which causes its acceleration. But as it starts accelerating, there's a resistive term which develops, which comes from the ionic cores, the contribution of ionic cores, and that tendency, or that uh, value of that resistive term, acts in acts to prevent this indefinite acceleration, and that is the reason why uh, the electrons attain some VF velocity, they saturate at that velocity, and they do not accelerate further. And at that value of velocity, the acceleration becomes zero. Okay. So one final problem from this section. Okay, let's have one based on Drude model itself. Okay, so question. Drude model predicts several properties correctly because A, there are no errors in the model. B, errors in the model cancel each other always. Option C, errors in the model cancel each other sometimes. And option D, thermal properties do not have a significant impact on other properties. So this question is based on the limitations of Drude model, as we discussed in the beginning of this session today. So the correct answer here is option B. Sorry, option C, right? So sometimes, if we are lucky, like we are in the case of thermal conductivity, when we compute thermal conductivity and so basically not just thermal conductivity, there's a term called so there is actually a quantity called not a quantity, but it's a law. It's called Wiedemann-Franz law, and what it says is that the ratio of K over sigma T. Okay, if we take metallic conductors and we, for each metallic conductor, we take the value of thermal conductivity, its conductance, and temperature, absolute temperature, right? This ratio is constant. So this is what the law says, and this constant is of the order of 2.4 into 10 to the minus 8 joule omega per second per Kelvin square. Okay, and now uh, if we so we know the expressions of K, the thermal conductivity, and sigma, the electrical conductivity, from the discussion we had, right? We know that K by sigma T. So first let's write the expression for K, that is 1 by 3 and root mean square velocity, actually, then tau and CVE, right? This is the expression for K. The expression for sigma is 3, no, there's no 3, sorry. Expression for sigma is NF E square tau divided by M, right? And then we have temperature T. And if we simplify this expression, we see that this is equal to 3 times Kb, the Boltzmann constant, squared divided by 2 times E square, where E is the charge on electron. And if we compute this, we put in the values for the Boltzmann constant and the charge of electron, and we will get this quantity to be of this order. Right? So if we look at the ratio of these two quantities, we see that we are quite close to the experimentally determined values, right? The Drude model and the experimentally determined values from the Wiedemann-Franz law, they agree with each other quite well. But the reason they agree with each other is because the CVE, the electronic contribution to heat capacity, this is underpredicted by an order of 10 to the 2. And similarly, if we look at the mobility, which is this factor now, so this factor is overpredicted by a quantity of 10 to the power 2. These get cancelled with each other, and we are left with this. Basically, all the limitations of this model go away in this particular case. So we see that the value that we get from here, it's very close to the experimentally determined values. So that's why but this cannot happen always, right? This is one of the situations, one lucky situation where all works out. So we see that the correct option is this one, that the errors in Drude model cancel each other sometimes, but they do not always cancel each other. That's why for some quantities we get a good prediction, while for others the prediction is not as accurate. Okay. So now let's get back to today's discussion. Okay, so we'll start with the concept of statistical mechanics. Okay, what is statistical mechanics all about? Statistical mechanics. And statistical mechanics, so the core idea is okay, before that let me just write the expression for one of the quantities that we computed last time. Okay, let's say that we had this thermal conductivity K, and we computed that the value of thermal conductivity was this. So now if we look here at this quantity, if we focus on this quantity, what does this quantity give us? It gives us the average velocity for all the particles, right? So the way you compute this expression would be that, let's say there are 100 particles, okay, 100 particles, and these 100 particles have velocities v1, v2, v3 up to v100, Now if we want to compute this Vrms square and then compute K, thermal conductivity, we will need to know all these properties, right? All these velocities. We should know all of them, and then Vrms square, it will be V1 square plus V2 square plus V3 square plus so on and so forth up to V100 square. And then you take the average of all these. Let's say there are 100, so we divide by 100. So this will be the mean square velocity. So unless we know the value of all these quantities, right, we cannot know what the value of this root mean square velocity is. And similarly the value for thermal conductivity. So this is, and in large systems, okay, I only assume that there are 100 particles here. If we take the example that we took last time, that in 1 meter cube, in 1 meter cube of a metallic solid like Ag, silver, right, it's a univalent atom, so each atom gives out one electron, and if we compute the number of electrons in 1 meter cube of this solid, it's of the order of 10 to the power 28. So when the dimensionality of our system is large, if we have this many particles, now imagine that what this sum would look like. We'll have to add 10 to the 28 terms and then take their average, which is not conceivable physically, right? We cannot do it for all practical reasons. So that's why, to avoid such difficulties, we work with other quantities, right? That's actually the whole concept or whole motivation behind studying statistical mechanics. It's to represent physical quantities as the most probable, or in terms of, right? In terms of most probable state. And this most probable state, this is what's called the equilibrium state. Equilibrium state of the system. Right? So what does this mean? Okay. So for example, let's take a simple example. Let's take a very simple example. And let's say that we have a system of two particles. Okay, so imagine a system of two particles. Okay, and let's say the energy, let's say that the energy of the system has to be 3E. Okay, this is just some random value for now. Okay, we will not bother too much about where this 3E comes from. There is just some unit energy represented by this epsilon here. Okay, this epsilon, it just represents some unit energy, and I am taking 3 times that energy, and I am putting a constraint on my system that my system, which has two particles, the total energy of my system should be 3 times epsilon, right? And what I'm further saying is that, no, this is all I'm saying, right? So if there's one base energy which is epsilon, or let's say there's zero energy as well, right? Totally zero energy, then we have an epsilon amount of energy. So these are different energy levels now. This one is 2 epsilon, and this one is 3 epsilon, right? So these are my energy levels, and I have two particles in my system. I have to arrange them in such a way that the total energy of the system should be 3 epsilon. Okay, the question is, how do we do it, and or what are the total number of possibilities in which we can construct the system, right? So if we see, if we put one particle here, okay, and one particle here, this is one obvious choice, right? This is one obvious choice because the energy corresponding to this particle is 0, and the energy corresponding to this particle is 3 times epsilon. So if we add the two energies, we have fulfilled this constraint on our system. So this is one way in which this configuration can be achieved, right? And is there any other way? What if we have the same system again? Okay, let me again redraw the system, the whole system, and let's say we have the exact same energy levels as before. This is 0 energy, this is epsilon energy, this is 2 epsilon, this is 3 epsilon. Now another way to arrange this system would be to have one particle at the energy level of 2 epsilon and one particle at the energy of epsilon, right? So in both the systems, in both these systems, we have two particles and the total energy of the system is 3 epsilon, right? So these configurations, these are called microstates. Okay, microstates. So microstate, these are distinct configurations which obey the constraint on the system. Okay, so this is like the total number of possible ways in which we can construct this system, right? So this is microstate, let's say 1, and this is microstate 2, and both of these configurations are, number one, distinct. That's the first characteristics, that these are distinct, right? We cannot confuse this for this. We know this is a distinct configurations. Here we have one particle in the energy level 3 epsilon, but here we do not have any particles here. And similarly, in this configuration we have particles in these two energy levels, twice epsilon and epsilon, but we do not have any particle here. So these are distinct from each other, right? And number two is that both of these obey the constraint on the system. Now what is the constraint on the system? The constraint on the system in this case is the total energy. Both of these microstates, they add up to the same energy, same total energy, right? So this is the definition of a microstate. Now if we look at in how many ways a particular microstate can be achieved, right? So here we are taking an assumption that particles are, let me write it, what the assumption is. So assumption is that particles are identical and distinguishable. Right? And this assumption is a big assumption. Okay? And it's because of this assumption that something fails. It's because of this assumption that finally the truth model becomes unsuccessful in predicting some of the properties. Right? So these are important to understand, these two words. What is identical and what is distinguishable. Right? What is identical and what is distinguishable. Right? So identical means same, right? Exactly the same. That there is no difference. Right? So identical means no difference. And exactly the same. And distinguishable means that we can tell two identical particles apart. Okay. So what does that mean? It means that, let's say we have two cricket balls. Yeah? Let's say this is a cricket ball. Okay. And let's say we have another cricket ball. And let's say we have another one. Let's say we have another one. Right? So these are all identical. There is no difference between one and the other. But they are still distinguishable. Right? We know that this ball is different from this ball. Different in terms of its identity, right? If we label them 1, 2, 3, right? This is ball 1, ball 2, ball 3. These are distinct balls. We cannot say that this ball and this ball is same. This is similar but not the same ball. These are two different balls, right? They are not the same ball. They are similar in every aspect. Like their size is the same, their color is the same. If I first show you one and then I ask you to close your eyes and then show you another, you will not be able to say which one was which was which, right? But at the same time, if I give you these three balls, you can tell, okay, this is the first ball, this is the second ball, this is the third ball. So in that way, they are distinguishable from one another, right? We cannot confuse, or a better way would be to say that if I have one ball in my right hand and one ball in my left hand, they look exactly the same. There is no difference in any of their attributes like color or size or weight, but still there is some attribute, like the ball which is in my left hand, it will continue to be in my left hand always. The ball which is in my right hand, it will continue to be in my right hand unless I change them deliberately. intentionally, right? So these particles, they are distinguishable and identical, right? And this is the case for all classical particles. Classical particles are identical and distinguishable. And naturally we would assume that there are other particles, right, which we call quantum particles later, which are identical, and in certain cases they may not be distinguishable, right? We may not be able to distinguish one from another in some property, right? Some property of theirs, it might not be distinguishable. Or the other way to say it is, we cannot come up with a parameter to distinguish those two from one another. There does not exist any such parameter in certain cases, right? So but in classical physics, which the Drude model is based on, we always this will always be the case, that particles will be identical and distinguishable. Now once we take this assumption, what does this assumption mean in terms of the microstates, right? So let's take this system again. So we say this is a two particle system. Two particle system. Right? And if we compute how many ways can we form this particle, this microstate, right? This is now the microstate. So in how many ways can this microstate be achieved, and in how many ways can this microstate be achieved, right? So the answer is simple. You have one energy state and you have two particles to choose from, right? So if we look at this microstate, if we look at one of the energy levels, say focus on one energy level, let's say 3e. Now we know that one particle has to go here, but we have two choices, right? Because there are two distinguishable particles. So when we focus on this one, there are two ways in which we can fill this state. We have two choices, right? So we can say that the number of ways, because once we fill this state, the other one is automatically decided, right? The other particle will go here. So there are two ways in which this microstate can be achieved, right? What about this one? What about this microstate? It's the same argument here, right? Because if we look at this microstate, I know that I have to fill one particle here, but I have two choices, because now my particles are distinguishable, right? So this can also be filled in two ways. Just a minute. Okay, so there are two ways in which we can fill each of these microstates. So these microstates are equally probable, right? The system can either be in this microstate or it can be in this microstate. because these are equally probable. And by probable I mean there are same number of ways in which this microstate can be filled, and there are the same number of ways in which this microstate can be achieved, right? Now let's see, if we increase the number of particles in the system, how does this trend evolve? Okay, and here the constraint is that total energy it's 3 epsilon, right? And with the same constraint, now let's increase the number of particles. Okay, now let's go to a 3 particle system. Or let me get rid of these and let's see. So this is our first energy level. This is 3e, this is 2e, this is e, and this is 0. Okay, 0, this is epsilon, this is 2 epsilon, this is 3 epsilon, and now we have 3 particles. Okay, with the same constraint, the total energy is 3 epsilon, right? So how do we achieve this, right? So in this case, what we can do is, first we can have one particle here, another particle also here, and the third particle can be here, right? The total energy is still 3 epsilon, 3 epsilon. So this is one way. What would be the other way, right? I just duplicate this and get rid of these. So what if we have 3 particles today, right? We can have all 3 here at the energy level of epsilon, right? Because then also the total energy would be 3 epsilon, right? So this is second microstate. And what's the other way? Is there a third way as well? Yes. So another way would be to have this system let me make them slightly bold to distinguish them. And now if I get rid of these, I can have a situation where I have one particle here, one particle here, and one particle here, right? Even in this case, the total energy is 3 epsilon, because one particle has 2 epsilon and one particle has single 1 epsilon. Total energy is 3 epsilon. So now, yeah. So I think these are all the combinations possible. Just a minute, let me just confirm. So these are all the possible combinations which obey this constraint, right? So now let's see what are the total number of ways. So let me call this microstate 1. Let's call this microstate 1. Let's call this microstate 2. And let's call this microstate 3. Right? They all correspond to the same microstate, right? The microstate is a state of 3 particles with a total energy of 3 epsilon, right? That is the microstate. The microstate concerns how these are distributed within the allowable energy energy levels, right? So what are the number of ways in which we can construct this first microstate, right? So now we know that there is one particle has to be in this configuration, right? Now this particle can be chosen in 3 different ways, right? It's similar to the case above. There are 3 different ways to choose this. So number of ways for first microstate, okay? That is what, 3 times. So there are 3 ways to choose this particle. Then there is only one way to choose these 2 particles, right? Because no matter what choice you make, the other 2 particles are already fixed. Once you fix one here, once you fix that one goes here, the other 2 have to go here, and the order will not matter in this configuration because they are in the same energy level. So it won't matter if you put one particle here, or if you put this particle here or this particle here. It will not make a difference. There is only one way to allot 2 particles to a particular energy level, right? So there is only one way. So total number of ways is 3. Right? Or let me make a table. Let's tabulate this. So we have microstate and then number of ways. Right? So for the first microstate, we have 3 cross 1, which is 3 ways, right? Now what about second one? What about the second microstate? Let's see this one. How many number of ways can this state be assembled, this microstate? So if we use the same concept again, we know that there is a certain energy level epsilon and all the particles are going there, right? So there's only one choice, there's only one way in which you can put all the particles here, and if you just consider other permutations like this particle here, this here, that will not matter because this is the same energy level, right? So there's only one way of putting 3 particles in a particular energy level. So the total number of ways is only 1 in this case. So for the microstate 2, there is only one way of constructing that microstate. And for this microstate, the third microstate, what is the total number of ways? So now here we have a choice, right? So if we consider this one, there are 3 ways of choosing this. So we have 3 particles and we have to put 1 particle here. So we can put either the first particle or the second particle or the third particle, right? So the total number of ways would be 3, because here we have we can choose this particle in 3 different ways, and then once we choose this particle, we are left with 2 more particles, and now I have to choose which one to put here, right, because these are distinguishable, right. So there are 2 ways in which this state can be filled. So one is filled here, this can be filled in 3 ways, and once we fill that, there are 2 more left, 2 more particles left, and now this energy state, I have 2 ways to fill this energy level, right. And then this energy level, there's only one way to fill it, because the remaining one will go there, that's fixed. I do not have any choice there, right. So 3 into 2 into 1, that is 6. So there are 6 ways to construct this microstate, the three microstate, right. Microstate 3, it can be constructed in 6 different ways. So it can be constructed in 6 different ways, right. We saw that in the first case, when we had only 2 particles, both of them had the same number of ways in which the microstates could be constructed. Here we had 2 ways, here we had 2 ways, but now we start to see that once we increase the number of particles in the system, we have differences in these number of microstates possible, right. So for first microstate we have 3 ways, for second microstate we have just 1 way, and for the third microstate we have 6 different ways in which we can construct this microstate, right. And now we will do one final one, which is for 4 particles, right. So 4 particle system, and the constraint will be again the same, right. The constraint will be total energy is 3E, 3 epsilon, 3 times epsilon, and particles are 4. Okay, now let's take again these levels, right, these energy levels, and let's say this is 1, and now we'll get rid of this, right? And let's say this is 1. Let me make a few copies of this, right. So how can now we fill four particles and these 3 energy levels such that the total energy of the system is 3 epsilon, right. And again, the obvious choice is put 1 here, 1 particle here, and then put all other particles, the remaining 3 particles, put them here, right. The total energy of the system would be 3 epsilon, right. Now what about, is there some other way? So we have 4 particles, right. So what if we put 1 here, 2 here, and 1 here? Right? This will also have the total energy of, no, this will have the total energy of 4 epsilon. No, this won't work. This won't work, right? Because the energy is increasing. We only need 3 epsilon energy. So we put 1 here and 1 here. Right? This also has 3 epsilon as the total energy. And the other thing we can do is, we can put 2 particles here or 3 particles here, and 1 particle here, right? So these are the only 3 ways in which we can fill 4 particles in this system in such a way that the total energy is 3 epsilon, right? So now let's calculate the number of ways. So how do we calculate the number of ways for this one? we calculate the number of ways? We can use the same principle, number of ways. Right? So if we look at this state here, there are 4 ways to fill this state, right? So there are 4 ways to fill the state, and then there is only one way to fill the remaining 3 in a single level, right? So first energy level, this one, there are 4 different ways to choose this particle, and then the remaining 3 we just put them here. There's only one way in which 3 particles can be put in one energy level, right? So the total number of ways is 4. Now in this case, what is the total number of ways in this case? In this case, okay, let's see this particle. We are looking at this particle. There are 4 ways of choosing this particle, right? Because now we have 4 particles, and for this particle there are 3 ways, right? Because once we fill one here, we are remaining with three ways, 3 particles in which we can choose to go here, right? So this can be filled in 3 ways, and after that there is a single way to fill these 2 into one energy level. So the total number of ways here, total number of ways is what? 4 into 3 into 1, that is 12, right? There are 12 ways to fill this microstate. And let's take a look at this one also. Number of ways. Right? Can you tell me what would be the number of ways here? If anyone wants to attempt, how do we calculate the number of ways? Does anyone want to take a guess?
Sir, 4.
Yes, exactly. Because if we look at this microstate, this can be filled in 4 ways, right? There are 4 particles and 1 energy level. So there are 4 ways to fill this one, and then the remaining 3, there is only one way to put them in a 1 energy level, right? So the total number of ways here would be 4, right? So okay, so in this case we had 3 different microstates, and we looked at the number of ways in which we can fill those microstates. So in the first microstate there are 4 ways, in the second microstate there are 12 ways, and in the third microstate there are 4 ways, right? So now just to highlight what we are doing here is that we had 2 particles, right? Then we had 3 particles, and then we had 4 particles. Okay, so here we had 2 microstates in the first one. We had 2 microstates. Here we had 3 microstates, and here we had 4 microstates. Right? And if we look at the numbers, right, the number of ways for these microstates, we had the numbers 2 and 2, right? For these microstates, there were 2 ways in which we filled one microstate and 2 ways in which we filled the other microstate. And for this 3 particle system, the microstates, the number of ways for the microstates, these were 3, 1 and 6, right? We can go back and check. This is what we obtained, right? 3, 1 and 6 as the number of ways. And for this case we had 2 and 2, right? And now for the 4 particle system we have 4, 12 and 4, as the number of microstates. So this is 4, 12 and 4. So what do we observe here? The observation is that as the number of particles in the system increase, right, as we are moving this way, the number of particles in the system are increasing, and the difference between the number of states for the most probable microstate, right? The most probable microstate here is this one, because there are most number of ways in which this state can be constructed. This microstate can be constructed. There are more ways. So this is the most probable one, right? So in terms of probability, if you think, there are total 10 categories. There are total 10 possibilities, right? To have this macrostate. So out of those 10 possibilities, six possibilities are there for a certain microstate. There is one possibility for some other microstate, and 3 possibilities for some other microstate, right? But the one which has the maximum probabilities, right? If you calculate the probability for this microstate would be 6 by 10, right? 6 divided by the total number of events. So here it would be 1 by 10, and for this microstate it would be 3 by 10, and here it would be 2 by 4 and 2 by 4, right? Probabilities. And here it would be 4 divided by total sum. Total sum is 20. For this one it would be 12 by 20 and 4 by 20, right? So we see that in all the cases there is one state which has more number of ways than other states, and this state is called the most probable state, right? So the observation now, so let me just write it. So these are, so here the most probable state is any state, right? In two particle system, it doesn't matter whether you go with first microstate or the second microstate, they are both equally probable. But as the number of particles increase, we see that there is a clear distinction between the most probable state and other states, right? So these are most probable states. Most probable states. Right? So now the observation is, as the number of particles increase, the difference between the most probable state and all other states, right, that difference increases. Now what do I mean by the difference? If you look at the difference here in this one, the difference is the most probable state has 6 ways, and the next probable state is 3, right? So therefore we have a difference of 3. Now in this case, where we have 4 particle system, if we look at the most probable state, that has 12 ways of constructing it, and the next possible or the next favorable state has 4 ways, right? So this difference is 8, and in the 2 particle system it is 0, right? So as you increase the number of particles in the system, you see that the difference between the most probable state and the other next favorable state, that difference increases, right? And remember that in our system we had how many particles? We had roughly this many particles, right? This is our system. Per meter cube we had this many particles. So in such a large system, the difference between the most probable state and the all other states combined, that difference is so large, like it's many times large than the all other states combined, right? So for example, what do I mean by that is, so here there are total 10 states possible, right? Here there are total of 4 states possible. Here there are total of 10 states possible. Here the total number of possible states is 20, right? So if you again, let's take the difference of most probable state and the total number of states. So this was between, this difference was between this was between the most probable state and the next favorable state. Now if we take the difference between the most probable state and all other states combined, now that difference is in this case, right, in this case again the difference is 0. 2 minus 2 is 0. In the 3 particle system it is what, 6 minus 3 plus 1, that is 2, right, 6 minus 4. And in the 4 particle system this is 12 minus 4 plus 4. Now we are combining all the other states and subtracting that from the the most probable state. This is 4, right? So we see that even this trend is increasing, right? So as our system goes to this many particles, this number of particles, these numbers become huge, right? So the most probable state, that becomes most dominant state of the system, right? So that state is what we call the equilibrium state of the system. So this is that is the state, the most probable state. That is the state in which the system, you will find the system most number of times. More than 99% of the times you will find your system in that state, right? So let's get rid of all this and write that most probable state is the equilibrium state of the system. Right? So now with that in mind, let's calculate what would be the number of states and what would be the most favorable state for n number of particles, right? We did the examples for 2, 3 and 4. Now we will go to general system which has n number of particles. Okay. So for a system, or let's call this n particle system, right? And let's have a diagram here to help us. So this is epsilon. Okay, now we don't know how many energy levels there are, and this is a question in itself: how many energy levels should we have, and what should be the difference in each energy level. But for now, let's just say that there are some r number of energy levels. Okay. This question will be clear later in the course. What determines what is the number of available levels, right? So for now, let's say that something like this, right? This would be ER minus 1, and that would be E1, and we'll have some E0 as well, right? Or let's say 0 or E0, doesn't matter, right? So this is now an n particle system, and we have R levels, right? R levels of energy, and we have total number of particles n, right? And there is a okay. So before that, let's look at what is the probability, not the probability, what is the number of ways in which a particular microstate can be accomplished, right? So let's say that there are okay, to be consistent with the notation, yeah. So let's say that there are n0 particles in this one, right? I don't know how many there will be. Let's say that this number is n0, and similarly there will be some number of particles, I don't know how many, and let's call this n1, and similarly there will be some particles here, right? Let's call this nr minus 1, and similarly there will be particles here, let's call this nr, right? So these are the number of particles in each energy level, and what I am saying is that there are n number of particles, right? That means the sum of all these particles should be equal to n, right? So I'll write that. It means that n0 plus n1 plus so on and so forth plus nr, this sum is equal to n, right? This is my first condition. And now my second condition is that what's my second condition? The second condition is that energy of this system is fixed, right? And I don't know how much that is, but that energy is fixed, and we will use that. But what I want to find out is for this particular microstate. Okay, now this in itself is a microstate, right? There are different energy levels, and there are n0 particles here, n1 particles here, and this many particles here, this many particles here. The question is, for this particular microstate, right, what are the total number of ways to attain this particular microstate? Okay, that is the question. This particular microstate that I have drawn here, what are the total number of ways in which this microstate can be achieved? Okay, now in the previous examples we were fixing first we in each case, these were simplistic examples, so we were basically figuring out how many ways. We just had to allocate one particle to each energy level, and then we knew that the system has 4 particles or 3 particles, so the calculation was a bit easier. But in general, for this system now, I do not know that there's a single particle anywhere, right? So I cannot use that approach. So I have to use a much general approach, and I will use this well-known result from probability, that number of permutations of n let's say objects, okay, if let's say n0 number of particles or n0 number of objects are of one kind, n1 objects are of second kind, and so on, right? Okay, so what that means is, to give you a physical representation, if I have 10 balls, let's say this is my ball, right? So if I have 10 such balls, or any, let's say how many, 7, 8 number of such balls, right? And we try to rearrange them. Is it possible to rearrange them in such a way that they look different? By rearranging, I mean if I just put this here and this here, and if I exchange these two or maybe these two, no matter what I do, the system is going to look the same, right? It will not matter, right? Every permutation is going to look the same no matter how I arrange these balls. Okay, so this is case 1. What is the case 2? Now let's say that I have same number of balls, okay, but 2 of them are let's say pink, right, and maybe two of them are green, right. And now in this case the rearrangement makes sense, right, because if I change this one with this one, I will get something like this, where this one would be here, this one would be here, right. So these two configurations are different, these two configurations are different, right. If I do the same thing, like I exchange these two and now it gave a different configuration. If I do the same thing for this, it will not give me a different configuration, it will still be the same, right. So that is very, so the number of permutations, when we say, if we read this statement what we wrote, the total number of permutations of n objects, n here is the total number of objects. Now in this case there are 1 2 3 4 5 6 7 8 number of objects, right. If n0, this is just some number, n0 number of objects are of first kind, for example this n0 can be pink, right, n0 can be 2 because 2 objects are of one kind, and then n1 objects are of second kind, let's say green, right, and n1 is also 2. So similarly, if we have such a system where we have total number of objects is n, out of which n0 are of first kind, n1 are of first kind, and n2 are of second kind, and so on, right. So what is the total number of permutations that we can have in the system? By total number of permutations I mean total number of distinguishing states, right. If we do the permutation, we see a different, we are able to distinguish those two, no two states are the same. What are the total number of ways in which we can do that? And the formula is this, right, that number of ways is equal to capital N factorial divided by n0 factorial, n1 factorial, n2 factorial, and so on, right. So if you look at what this means, it means that these two objects, right, so first of all let's say that all these n objects were distinct, right, different colors, then there would be n factorial ways of arranging these particles, right. If they are all different, we can all distinguish them from one another, then there will be n factorial ways in which we can arrange them. Now if two of them are same, right, we can internally permute these two in another, let's say this number is small n or n0, let's say this is n0, number of particles are of one kind, we can internally permute them in such a way that the system does not change, right. For example, let's look at this configuration, right, this one. If I change again, interchange these two pink states, the system will not change, right. So what this formula does is it divides the total number of permutations. If all the objects were different, then this would be the number of permutation, and it divides them with the permutations that are of one kind, which will not change the identity of the system. And similarly for green balls, there will be n1 number of permutations, so it just takes away those permutations from the system. Okay, similarly we will use this concept here in exploring this n particle system, right. And here if we use the same system here, then the number of ways for this microstate, this particular microstate, it will be what, n factorial, where n is the total number of particles, divided by n0 factorial, n0 factorial, n1 factorial, and so on up to nr factorial, right. It's the same situation here, because if you permute these n0 number of particles, if you permute them amongst themselves, it will not make any change to the system. It is the same system again, right. Similarly, these can be permuted among each other. and similarly for all other states. So this is my formula now. This gives me the total number of distinguishable ways in which I can distinguish one microstate from the other microstate. Okay, these would be the number of ways. So let's write this properly. So I will now, for the n particle system, number of ways, and I will call that omega. Okay, this number of ways, omega, this is equal to n factorial, n factorial divided by n1 factor, n0 factorial, n1 factorial, so on up to n r factorial, right? So this is the number of ways in which we can arrange this microstate, right? And now let's apply log to both sides. Okay, applying log, to both sides, we will get what? Natural log. So I am using the natural log here. Okay, log to the base e, that's the log I am using here. I'll get log omega is equal to log of this thing on the right hand side, right? But I know that log a by b is log a minus log b, right? So this will be log n factorial minus the natural log of this thing, n0 factorial, n1 factorial, so on up to nr factorial, right? And I have used here the condition that log of a by b is equal to log a minus log b. Okay, so we can simplify this further, because now we know that log of product is equal to sum of logs. Okay, and I'll use that. So log omega is equal to log n factorial minus log of n0 factorial plus log of n1 factorial plus so on plus log of nr factorial, right? And what I have used here is that log ab is equal to log a plus log b. Okay, so now I have a situation where I have a factorial inside a log. I have log of something factorial. Okay, and there is a formula which is called Stirling's approximation. Stirling's approximation, which is what? Which says that log of any x factorial, it is approximately equal to x log x minus x. Okay, and this is a very good approximation. Okay, this Stirling's approximation, it works very well even for small values of x. Let's say if x is 5 or 8 or 10, this gives a very good approximation. So in our case, we know that this n is going to be pretty large, right? So we can replace this approximation symbol by equal to, because there will be very minute difference which is negligible, right? So now if we use that in our above formula, what we will have is log of omega is equal to, so let's first apply this to this term, log of n factorial, we will have n log n minus n, and then we will apply it to others. So it's better to write this whole term in a summation form, otherwise So we'll sum it from I goes from 0 to r, okay, and then we'll use this approximation that will give us ni log of ni minus ni, right? So I have just applied this Stirling approximation to every term here, and then I am taking a summation, right, from I running from 0 to r. So for example, if you look at what is the value of this at I is equal to 0, it will be n0 log n0 minus n0, which is log of 0 factorial, right? Log of n0 factorial, and which is this term here. And similarly we are doing it for each I. Okay, so now this is our number of states, right? Number of micro states represented in terms of a log, right? And now the most probable state would be which one? It will be the one which maximizes omega, right? Because omega is the number of microstates, right? So we have to maximize omega. That will be our most probable state. So how do we maximize omega? We maximize omega right. So when omega will be maximized, at that time just a moment. So if omega is maximum, right, if omega is maximum, then what happens? Then the derivative is 0, right? Because at the point of maximum or minimum, the derivative goes to 0. And if we look at what omega depends on, this n here is a constant. It's the total number of particles present in the system. So is this. So the only variables here are ni, right? These ni are the only variables. So when omega is maximum, then the derivative of omega with respect to all ni should vanish. That is the point of maximum. So what we should have is you see, if omega is maximum, first I want to point out that if omega is maximum, then this factor is also maximum, right? Because log is a monotonously increasing function. If you have looked at the graph of, let's say, if this is x and this is natural log of x, the graph goes something like this, right? So we see that this is monotonously increasing function. So let's see, log x graph. Oh, you may not be able to see this, but yeah, this is the log of 0. Log of 0 is 1, so it will pass through here, right? Oh sorry, log of 1 is 0, so this graph will pass through this point, right? So this is the plot of log, okay? So log of 1 is 0, right? So but the point is, as x increases, log x also increases. So if x is maximum, that means log x is also maximum at that point. So if this holds, then del of ln omega with respect to each ni, this should vanish, okay? And if we look at what this means is, okay, so we are running a little short on time, but this is our first requirement, that this derivative should vanish. And second requirement is that uh, so summation of, if you look at the total number of particles is fixed, right? It does not change. So which means that if we take the summation, I runs from 1 to r, del of ni, this should be 0. So what it basically means is, since the number of particles is fixed, if you take uh, yeah, so if you take this particle here, then the number of particles here will be n1 plus 1, and here it will be n0 minus 1, right? So this lost one particle, this energy level gained one particle, but the total number of particles will be the same, okay? Because here we have a plus 1, here we have a minus 1, so these two changes cancel each other. And similarly, if you sum those changes for all I, that should be 0, right? So this is our second, it's a constraint now, right? This is a constraint that must be obeyed at all times. And the third constraint is that the energy of the system is fixed, okay? Energy of the system is fixed. And how do we calculate that energy? So change in energy must be 0. If energy is fixed, change in energy must be 0, and this will be computed by this factor, right? This is the change in energy for one microstate, okay? So if we now multiply that change in number of particles by the energy level of that by the energy of that energy level, that the sum of that should be 0. What I mean by that is, if one particle goes from here to here, so the energy here now would be whatever it was earlier plus epsilon 1, okay? Or let's say two particles, if two particles go from here to here, right, from n0 to n1, two particles go there, then the total energy of the system goes up by this one and it goes down by this one, right? Okay, so now if the energy of the system has to stay constant, then twice epsilon 1 minus twice epsilon 0 should be 0, right? Only and only then will the energy of the system remain constant. So similarly, if you do this for all the energy levels, you will get this, right? This constraint here. So this basically is conservation of energy, right? This is again a constraint on the system. Now if we solve these three equations together, this is now, so this is an optimization problem, if some of you are familiar with this optimization problem. Am I audible? Hello? Hello? Am I audible? Okay, let me try to finish this recording. So I was saying that this is an objective function now, and these are the two constraints, and we can use Lagrange's method, which basically solves a constraint optimization problem. And there is something wrong with the network. Okay, we are back. So if we solve this system, the solution comes out to be something like this, that Ni is equal to n over p e to the minus epsilon I over epsilon I over kBT, right? Where this 1 over k by t, here in this factor 1 over k by t, that comes out to be a Lagrange parameter, and this p is equal to summation of I runs from 1 to r, 0 to r, so basically sum of all these states. So this is whole to the raised to the epsilon, sorry, e, the exponential number. This is what p is, and this is called a partition function. Okay, so these are all just mathematical steps. This comes out naturally, but the important thing to notice here is that this formula, it relates ni. Okay, ni is now the number of particles. Ni now is, it's the number of particles in the energy level ei, right? So it relates these two things. It relates, this formula relates the number of particles in each energy level to the energy level of the energy of that energy level. So basically, given an energy level, we can find out what is the number of particles in that energy level, right? And if we try to plot this function, the plot looks as follows. Okay, the plot looks as follows. Draw a cut at the top. This is what the plot looks like. These are the energy levels, and this is the number of states, right? So for E0, this starts from E0, E1, sorry, epsilon 0 up to epsilon n, and the particles go from n0, n1 to, let's say, nr. Sorry, it should be r here because we had r levels, right? So this is what the distribution of states looks like, right? And so this distribution of states is valid for a particular temperature that is given here, right? T. So this holds for a particular T. So if you change T, let's say there is some other temperature now, this plot will change like this. Okay, something like this. Plot this, something like this. Okay, this will be at T2 and this will be at T1. Okay, so at different temperatures we will have different distributions of particles in the states. Okay, and the question, the point is, if we take this, if we see how the distribution of states changes as we change the temperature, right? So something like, if we talk about something like dni over dt, right? How the number of states change, how the density of these states changes as we change temperature. So this factor here, when we use this Boltzmann statistics, so these are called Maxwell-Boltzmann statistics, right? This distribution, it's called a Maxwell-Boltzmann distribution. So if we look at this factor here, this is what runs the Drude model. Okay, the Drude model is inherently based on this statistics. And the point is that this statistics, if we look at this factor is what creates the problem in the prediction of properties using Drude model. Okay, so actually the number of states do not change as predicted by the Maxwell-Boltzmann distribution, and that is because we are again the particles that we are considering are electrons, right? And we assumed that these particles are distinguishable and identical, and somewhere there lies a problem in those assumptions, right? Because electrons are finally they are quantum particles, right? They are, and we are treating them like classical particles. That's why this problem arises. That's why there is a discrepancy. So this factor here, when computed using Maxwell-Boltzmann statistics, gives us a trend that is not consistent with that observed in electrons. And if we have to observe the correct trend that is experimentally found in electrons, we need a better estimate or better way of computing this term, and we will compute it in a different we'll take a different approach, which is called Fermi-Dirac statistics. And this quantity computed using those statistics that are much closer to the actual experimentally observed trends. Okay, and this is the reason why this Maxwell-Boltzmann distribution does not work. Okay, so I'll conclude here this week, and in the next TA session we will take it up from here, and we'll look at the introduction to quantum mechanics and quantum particles, and then gradually we will go into Fermi Dirac distributions. Okay, so thank you so much for being here. Thank you so much for listening. Bye.